Okay, so welcome back to another video. Here we have an integral from -1 to +1 of the square root of 1 minus x squared times the natural log of 1 minus x squared and then divided by x squared dx. This one's quite an interesting one. So we have a natural log, we have a radical function, and we just have the square, or not square root, x squared. So combination of three different types of functions on one integral. So this one's actually not going to be as bad. So it's actually just apply a little bit of some, u-substitution. There will be some trigonometric function / substitution involved as well. So it's a combination of both those two different types of substitution we'll be using. And then a nice little integration by parts by the end that will actually, help make things a lot easier to simplify. Well, easier being loosely, I use that term loosely. So not a lot needs to be said, so you'll see where I'm going with this, and it'll make things a whole lot interesting and easier once we go forward. So with that one, I should jump right in. So first, what I like to do is notice that this is actually an even function as we put everything for -x, and you're still going to get the same thing. But in this case, that means what I can write this as a double of 2 times the integral from 0 to 1 of the square root of 1 minus x squared, then ln of 1 minus x squared, and then divided by x squared dx. So now here's our little substitution we'll be doing. So when we actually do this in y squared, we'll let y squared equals 1 minus x squared. So if I want to solve this by itself, I have x squared then equal to 1 minus y squared. Then differentiate both sides. So I have that 2x dx then equal to -2y dy. And so next thing what we'll do is that what we want to do is to get the dx by itself. We're actually going to have to, of course, just divide the 2 to both sides. Replace the x from here after we get this variable by itself. And notice that dx is then simply equal to -y divided by the square root of 1 minus y squared and then dy. Okay? So then plugging all this back together, so then what we have here is that capital I, we're going to call that capital I over here, is going to be 2 times the integral. So you change your bound, so we'll plug in the new bound, so that means I have that 0 is going to be on the top and 1's on the bottom of y, then the natural log of y squared, then divided by 1 subtract y squared, then substitute the dx differential, so -y divided by square root of 1 minus y squared, and then dy. Okay? So with that, now we can actually simplify some things up, of course, as you can tell, that for one thing, the bound's going to have to be switched, so that becomes a negative, but then that negative from the -y is going to cancel that out. And so we simplify things out even further, and also another thing is that the y squared based on the natural log, I can move that 2 outside to the front, and so that's still constant, so I can also move that outside that, so that means that'll become a 4. And then we have an integral from 0 to 1 of then y squared, so everything just simplified together, times the natural log of y, and then we have that this is going to be 1 subtract y squared to the power 3 over 2 and then dy. Okay. So now with that, let's actually perform yet another u-substitution. So we're actually going to be doing some trigonometric substitutions over here. So then we have that y, we're going to let y equals sine theta, and then dy then is going to equal cosine theta d theta. So now putting all this back together, so then I have 4, then the integral, so of course we have our new bounds, that's going to be 0, and then pi divided by 2. Then we're going to just substitute things back together for sine theta. So that means that's going to be sine squared theta. Then the natural log of sine theta. All this being divided by cosine cube of theta. And then now just substitute the dy differential. So times cosine theta, then d theta. Then what we can do here is, of course, this simplifies some things out. For one, I have those cosine thetas cancel, so I have a cosine square on the bottom, and then sine square over cosine square, that's of course tangent square, and then yep, that's it with that so far. So 0 and pi over 2 of tangent squared theta, then multiply by the natural log of sine theta, and then d theta. Okay, so now tangent squared theta, we can simplify that even further. That has a nice identity to say that's the same thing as secant squared theta subtract 1. So now 4 times the integral 0 to pi over 2 of, natural log of sine theta, and then multiply by secant squared theta subtract 1, and then d theta. Okay, so now with that being the case, so let's actually distribute the natural log sine theta into all this. So now we're actually going to have this in terms of like a sum or rather a difference of integrals. So we have 4 times the integral from 0 to pi over 2 of, so secant squared theta of the natural log of sine squared theta d theta, and then subtract 4 times the integral from 0 to pi over 2 of natural log of sine squared theta and then d theta. All right, so now this one is, we're gonna treat that as a given. So you can actually, there's actually tons of like resources out there, videos out there that actually go through this evaluation. So we're gonna treat this as a given, and you can actually look this up yourself. So we're gonna treat that as a given. I know I said that too many times, but this is actually gonna equate to the value of negative pi divided by 2 times the natural log of 2. And then now the next thing is that we actually have to calculate this integral over here. So this is where I mentioned that this is where the handy substitution, or not substitution, the handy integration by parts. So we're gonna choose our u and then choose our dv. So in this case, we're gonna let u be the natural log of sine theta. And so differentiate, so du is then equal to 1 divided by sine theta. Differentiate that, so of the inside, so cosine theta. So cosine theta or divided by sine theta, so that'll be cotangent theta d theta. And then choose our dv, we'll let that be secant square theta d theta. And of course, take its antiderivative, it's just gonna be tangent theta. Okay. Now just plug things back together. So then we have 4, then inside is going to be then u times v, so tangent theta multiplied by the natural log of sine theta, and then evaluate this from your bounds from 0 to pi divided by 2. Then subtract with the integral, so 0 to pi over 2 v times du. So tangent theta, cotangent theta, again, just use the identity with sine over cosine and then cosine over sine. You're going to see that they both cancel, and it's just simply just going to be just 1. So then that's just going to be simply just be d theta. And so we'll figure that out, and then just leave that the last part 4 times that. So then add this with 2 times pi times natural log of 2. Okay, so actually for our bounds, we have to calculate over here. So this is actually just going to approach simply just 0. But of course, the issue arises is that you can't just simply just plug it in like that, because it's actually just going to get some undefined numbers. So in this case, what you would need to do, and I'll leave this as an exercise so you guys can validate, is that you treat this as a limit for both the bounds. And then you're going to, of course, get something in terms of an indeterminate form. So you're going to have to apply L'Hopital's rule to actually get that as the limit approaches. So of course, this entire thing is simply just going to disappear to just simply just 0. And then over here, that's pretty easy to calculate. So that's just negative 4 and then multiply by, so just plug in the bounds. So that's just pi divided by 2 and then 0, so 0. And then add this 2 pi natural log of 2. Therefore, the final answer simply is just going to be 2 pi. So I actually just took a step ahead and just distribute, multiply by the natural log of 2, and then subtract 1. So with that, that is our final answer to our integral. That's a lot of crazy things going on over here, so many substitutions, and then just finish it off with an integration by parts exercise. And something like this, of course, you have to apply with the limits in that sense, and not just treat it like like a given, that sort of thing, as I just mentioned. So with that, there you have it. And yeah, that's pretty cool if you ask me.